Good morning. At the end of last week, I wrapped up our discussion about perturbative quantum gravity, kind of in the standard formulation as you're used to, from quantum field theory on Minkowski space. I wrote down the propagator of the theory in a specific gauge, in harmonic gauge, and also gave you a little flavor of what it'll take to write down a higher, well, 3-valent and higher order vertices. So this looked considerably more complicated than of some other theories. We also saw that as part of the symmetry structure of a general relativity, the necessity to gauge fix arises when you want to do the path integral, because otherwise you're integrating over many directions which give you infinite contributions, but which are not associated with different physics. And essentially, roughly speaking, what you'd like to do is to split up the underlying configuration space into kind of gauge directions and physical directions. And this is always possible locally, but usually meets obstructions globally. But we're not going into the difficulties that arise there. However, all right, the last customers are arriving. Now, then we looked at another feature of the perturbative series, a rather unfortunate feature that arises that we could trace back to the dimensionality of the coupling constant, which is of mass dimension -2, as we saw. And just by a simple kind of dimensional argument, you could already see that at higher order in the coupling, so G Newton, necessarily higher and higher orders of any momentum cutoff will arise. So that looks highly divergent unless, of course, by some miracle, cancellations occur in any order of perturbation theory. But I also told you that this is not the case. So in that sense, this way of writing down a quantum theory of gravity is not consistent above a certain energy scale, because then simply you have many, many terms you would have to take into consideration in your perturbative series, and they occur with, they're multiplied by powers of lambda divided by Planck mass. And these are only suppressed as long as your lambda is far away from the Planck mass. Otherwise, they will all contribute. And in order to fix kind of the renormalized couplings in front of all of those, you would have to make an infinite number of experiments. So in that sense, you don't get a deterministic theory. Yes?
So why not propose this idea of ultraviolet safety?
Asymptotic safety. Yes, that's the question. Can you still, in this conservative framework, make sense out of it? And so the basic answer is you might be able to make sense out of it if, of course, this, you need to know various things in order to understand what I say now. If the theory has another fixed point apart from the Gaussian fixed point at Gn equal to 0, if such a fixed point exists, then you might be able to define the theory at this fixed point. And actually, some recent research that has been done suggests that there might be actually such a fixed point. So you might get away with these rather conservative tools, quantum field theoretic tools, in quantizing gravity. But I hope to get back to this point at some later stage. So what we are talking about now is just perturbation theory around Minkowski space. And that has the properties I just described to you. Now, as I also mentioned, it doesn't stop you in principle from using this perhaps as a calculational tool, as what one would call an effective quantum field theory. So with effective quantum field theory, one means kind of the modern attitude one has about quantum field theories, which is to say, well, there are valid descriptions for a certain energy range. And to illustrate this, excuse me, take an example like QED. So QED is one of the first, well, examples you learn how to work with when you study quantum field theories. And of course, it's a beautiful theory, and it is very well tested and valid within its range of applicability. Now, when you come to high energies, it turns out that QED is no longer an appropriate description because other degrees of freedom get excited. And this would be, for instance, the W and Z boson. So if you reach energies of 80 GeV or so, then, well, your QED breaks down in the sense that it's not anymore the correct description for scattering processes. You have to take new excitations, new Feynman diagrams into account, and all of a sudden you are in the electroweak theory. So you'd say, well, QED is a beautiful theory, but it has just a limited range of validity. And, you know, that's, well, that's just the way it is. And beyond that, you'll have to look for another description. But it still is a valid and good tool in that limited range of applicabilities. That's what I wanted to say. And in principle, one can take an attitude for gravity too, that as long, you know, as one stays away sufficiently far from the Planck scale, well, it will just be an effective field theory description. The next question that arises is, are there actually any physically interesting effects that are not covered by the classical theory, but are genuine quantum effects that this effective field theory would enable me to describe quantitatively, and I could go away and measure in nature. The answer to this latter question is, well, that might be difficult. Although, in such an effective field theory framework, you can do computations, which are seemingly well-defined, but effects that you can compute tend to be just so minute that they're, again, totally out of the range of what we can reasonably expect to be able to verify or measure in nature. So, for example, people will try to compute, say, corrections to Newton's law. And you do indeed find first-order quantum corrections. What you then find is that they are of the order Planck length squared. So just correction to the classical Newton law. So they're well-defined computations, well, seemingly well-defined that people make. But then the result is just so ridiculously small, as I said again, that you can just say, well, what does it do for me? Is that a reasonable, physical, observable I should attach any great significance to? Perhaps the answer to this is no. So in that sense, yes, you might have a nice, effective field theory description below the Planck scale, but what it does for you is somewhat unclear, to say the least. Now, these and other considerations led people to, for some time, to question that the type of quantum theory one is considering, namely this perturbative construction around Minkowski space, may simply not be appropriate. Is one doing something fundamentally wrong? The question gets asked, for instance, in postulating, just starting, writing down this split in, G mu nu equal to Minkowski plus a small perturbation. And indeed, there are some things one might question here. So this was our split, the one we worked with at the beginning of talking about perturbative gravity. Well, first classically and then quantum mechanically. So we said, well, this is our general metric, Lorentzian signature metrics. This is a Minkowski metric. And this defines what I mean by F mu nu. But if for some reason F mu nu is small, if I'm in a situation like this, then I can systematically expand in powers of F mu nu. And therefore, the coupling constant. Now, of course, you might wonder what happens if you get two rather strong gravitational fields. Then clearly the approximation F mu nu small would no longer be valid. We could say, well, nevertheless, of course, what is wrong with this equation? I mean, this just defines f mu for me, never mind whether it's big or small. Well, what is wrong is what you then subsequently, how you subsequently treat this f mu. Because you think of that now as a linearized field, and consequently, you think also of the entries of this matrix array, this tensor, as taking arbitrary values on the real line, each one of them. Now, what's wrong with this? Well, what's wrong with this is that here, this was a metric of a particular signature, which entails certain constraints on the range of the entries of this matrix, which constrain it to have a specific signature, namely minus, plus, plus, plus. And that's not compatible with arbitrary values of all the entries, because they might lead to arbitrary signatures, or even, of course, things like a vanishing determinant. Right? So certainly what we have here is a constraint which says, well, I'm in the appropriate sector with regard to the signature of this metric, and the determinant of this is smaller than 0. And of course, what's also not possible, I mean, what's not allowed classically is for this determinant to vanish. Right? Then also space-time volume vanishes. That just creates a singular situation from a classical point of view, which you never consider. Now, people then say, well, look, if I write down a perturbative expansion like this, then usually, well, these are just arbitrary. I consider them as just, linear fields. So they can just take any value they want. But clearly, this violates the signature condition, which tells us something very essential about, well, is an essential part of why this is a metric and why this has a certain physical interpretation. So by ignoring this, I might get myself into trouble. So can I think of alternative quantizations that are less nonchalant? So here we had our perturbative, excuse me, I'm still in the perturbative regime, our perturbative quantum gravity ansatz, which usually doesn't impose any restrictions on these f's. Which is clearly incompatible with this inequality. So one says, well, there's something intrinsic about this. Can I think of quantizations which respect such an inequality on the G mu news? And actually, a part of the question that just was asked by you, Tibor, is, well, maybe there's also something wrong with the kind of ground state or vacuum state I'm perturbing around, so Minkowski space. So the question is here, so are there alternatives? And perhaps we are also not are we perturbing around the wrong vacuum? Well, what this leads one to is what people usually call a non-perturbative quantization. So that seems like one of these magic words, non-perturbative. But what it really means is, well, it's not perturbative. So it's not that what we have been discussing with the split here. So, and otherwise, well, you have to fill in the details of what you mean by non-perturbative. I mean, one characteristic feature of non-perturbative is that you say, usually you will look for a quantum framework where you're including, in a natural way, configurations that are very far from Minkowski space. Okay, so you say, well, let me take these into account, and maybe they're important in setting up my quantum theory. So let me write this down here. This is a remark. Maybe we should be thinking about some version of a non-perturbative quantization. And this will include, typically, configurations far away from any classical solution. The prime example, of course, exactly being the Minkowski metric. And of course, what I mean by far away also will need to be specified. Certainly nothing like, eta mu plus a small tensor f mu. Yes? Yeah.
And when we assume that f mu is a small,
yes,
is something
yes,
small,
yeah.
Why there was no problem in the determinant of g mu less than 0?
No, then there is no problem. If f mu is small, then of course you're somewhere just perturbing in the vicinity of the Minkowski metric, which of course has the correct signature, and it will satisfy this. The only problem you start running into, if now f mu entries become of the order 1, you see, and then you can just run also through zeros of the determinant of g mu if you don't have any further restrictions on f mu.
Because to me it looks like it's a matter of the sign. So
What's
it
the
could
sign?
be like a very big number, but it's negative. What's the problem with that?
Of what, the f's?
Yeah.
Well, it depends on which entries you're looking at. I mean, you're looking at entries of a 4x4 matrix, and I'm just claiming that for arbitrary values of f mu's, you will generally run into zero, first into a zero of this, and then into some region where this might be positive.
Okay.
But if that is the case, then it has no longer the interpretation, the classical interpretation of a space-time metric of, well, the signature we attach to that object classically.
So what you're saying is there might be a problem.
Well, indeed.
There is a problem, because you're summing over all.
Well, there might be a problem. Of course, you could say, who knows what I should be doing in the quantum theory? Maybe I should integrate over all these things. Yeah, but then you're widening your scope considerably. I mean, I would say what people sometimes consider is, well, in the quantum theory, can I maybe get away with including boundary points, that correspond to that g mu equal to 0 in some sense, but not including whole sectors, of course, of other unknown physics, that would hugely expand this configuration space. Of course, in the end, it's an open question of what you should and shouldn't do in the quantum theory. Anyway, that's a criticism people have leveled at this decomposition. So there are clearly potential problems. And we have already seen that the perturbative theory doesn't really do what you would like it to do. So you're looking for reasons, for good physical reasons, what you did wrong in getting there in the construction. So then people, you can say with hindsight, they try and look for explanations. So what got you there, what was maybe not a good assumption you made on the way. Okay, so now how to do this concretely will be the subject of the rest of these lectures. And as I announced, what I'll start with this week is covering what is called kind of the canonical construction of a quantum theory. So canonical quantum gravity, as opposed to a non-perturbative path integral approach to quantum gravity, which we'll look at next week. Now, in order to define the setting somewhat of what this is going to mean for the gravitational theory, I'll backtrack a bit and remind you of some structures in finite dimensions that appear when you quantize systems canonically. And in addition, then that's the second step, what you have to take care of when you quantize canonically a system that has gauge symmetry in it. And that will bring us to a discussion, a very important discussion, of the so-called Dirac formalism, of how you deal with constraints in the theory. They accompany the presence of gauge symmetries, and how this translates into a description for the quantum theory. So that is how I will start. So we start by making some baby steps and going back to Hamiltonian mechanics. Because really most of what I have to say can be beautifully illustrated in this much simpler framework and will be familiar to you for the kind of the standard dynamical system, but perhaps no longer familiar to you once we start introducing gauge symmetry, even in finite dimensions. Okay, so now I'm talking about a system with n degrees of freedom here, and my starting point is some general Lagrangian where I'm summing over I ranging from 1 to n. This is this number of degrees of freedom. And I have a standard Lagrangian m half qi dot squared minus v of q. Some potential depending on the coordinates and not the velocities. Now, in order to get to a classical Hamiltonian formulation, I perform a Legendre transformation, which amounts to, operationally, first, my defining momenta, so canonically conjugate momenta to the q's, canonical momenta. They are called little pi, and by definition are given by partial derivatives of this Lagrangian with respect to the i's velocity, and therefore are just equal to m qi dot. Just looking at this expression here. Now, and how do I get to a Hamiltonian from the Lagrangian? That's also very simple. I rewrite my Lagrangian as a function over I, pi qi dot minus h. And this h, just this equation defines my Hamiltonian. So that's the Hamiltonian of my finite dimensional system, which is written as a function of the q's and the p's. And for this particular case is given as 1 divided by 2m, p vector squared, so this is just a vector over all the i's, plus v of q. Okay, now I've transformed everything to a dynamical problem on phase space. And the phase space that has already appeared in some of our simple examples is spanned by these p's and q's, and it carries an additional structure, these canonical Poisson brackets, qi, where the fundamental brackets are qi with pj gives you delta ij. And let me write them out for completeness. The Poisson bracket of a qi and a qj is 0. And so is that of a pi with any pj. Everything, the dynamics, takes place on this phase space. And I'm just assuming that the configuration space was an Rn. So this phase space, let me call it curly S, is therefore an R2n. So this has n coordinate directions, and n momentum directions. And these Poisson brackets are also sometimes described as a symplectic structure. So this carries canonical symplectic structure. Well, and the symplectic structure knows something about the fact that some of these coordinates are obviously that there are some of these the coordinates on phase space are coordinates qr, and some of them are p's, momenta p. So these are, of course, exactly what gives rise to the Poisson brackets. I mean, it's just another way of saying I have these Poisson bracket structures, and it gives the set of all functions on phase space, on this phase space, an algebraic structure, namely that of a Lie algebra, because you see, you take just two arbitrary functions that needn't even be polynomials, you stick them into the Poisson bracket, you get a third one. Of course, it's an infinite dimensional space, so say C infinity, let us make them just smoothly differentiable, these functions, under the Poisson bracket are turned into an infinite dimensional Lie algebra. And the reason for emphasizing this structure, as we'll see in a little bit, is that you may wish to take, I mean, quantization is always, the wish to take over as many structures, for example, algebraic structures, over to the quantum theory in some way. And the question will arise, can we carry over this kind of characteristic algebraic structure that is there on phase space, on the phase space function? To what extent can we carry this over to the quantum theory? Okay, so this is a little bit, so formally, I can write things like that. So the Poisson brackets have as arguments, well, they can take as arguments any old phase space function and map it into a third one. So this is what I can write. It takes kind of the Cartesian product again into the phase space functions. And this relation, this algebraic relation, obeys a few nice properties. F Poisson bracket with G is minus G Poisson bracket with F. This is the antisymmetry of the bracket. And it's also linear. So for example, let me just write it this way without loss of generality. If the second argument here is some function g plus lambda h, where lambda is just a real number, then this is the same as f Poisson bracket with g plus lambda f Poisson bracket with h. So that's linearity in the arguments. And lastly, I have a Jacobi identity. That means if I have nested brackets like this, so I have a G with an H, and I look at its Poisson brackets with F, if I then cyclically permute these three arguments, they add up to 0. G, H, F plus H, F, J equal to 0. This is Jacobi identity. Oops. Now, you've probably all played around with these Poisson brackets, you may not have written, exhibited kind of the bare bones of their structure in this way. But let us see, now get to some more familiar expressions. Now, in general, if you're on a space with a symplectic structure, taking the form of such Poisson bracket relations, it doesn't have to be necessarily an R2N. It could also have a nonlinear structure. So such phase spaces also exist and are also relevant in physics. What you always can do, however, even if you're working on a curved phase space, you can always find locally coordinates such that everything looks locally as if you were on a flat R2N with coordinates Q and P, obeying these fundamental relations. The fact that you can do this is called Darboux theorem. So if you're just on a general phase space, you know that always locally, you can just rearrange things just by a coordinate transformation on phase space, so that these brackets kind of have the canonical form. And in terms of these canonical Q's and P's, the Poisson bracket takes, well, a specific functional form in terms of first derivatives of these functions, namely, so in canonical so-called Darboux coordinates, an F, of course, I haven't written out the arguments. Of course, it's a phase space function, so it depends on Q's and P's. Now let's assume that these are Darboux coordinates already. Then you can simply compute the Poisson brackets by looking at the partial derivative of f with respect to qi multiplied into the partial derivative of g with respect to pi minus the whole thing antisymmetrized minus del f, del pi, del g, del qi. And that might be a form familiar to you. So in case your phase space is already of this form, as would be for instance, a simple example we've chosen, then of course, this is a legitimate way of writing the Poisson brackets globally. So this will be valid everywhere. Yeah, there was a question?
Don't you need also on the production and the Leibniz rule? Because otherwise it's not define the Poisson bracket without the Leibniz rule?
Well,
So these three properties probably not enough.
These properties are not enough. Well, I'm already, of course, sitting on a space of functions, and multiplication is already defined on this space of functions.
But Poisson bracket is not.
What?
So you need to have Poisson bracket f at g times a, I think. If it's not defined that.
You mean that it's distributive on a product x?
Yeah.
It must be, well, this is the way usually the properties get written down. So that means probably that I have already made the assumption that I certainly can multiply. Well, certainly what you're saying is correct, right? That this is how it works. I mean, that it's distributive. If that was a function, then I would, of course, again, exactly get a Leibniz rule. I can write it down. So, what am I doing? Mid, where down, where is down? Okay, so I think that's what you have in mind. So this is, it's not contained in the above. This is G, F, G, H plus F, H, G. Of course, here it's still a relatively simple case. Everything commutes. I mean, also in the quantum theory later, one has to be careful to where to place, these factors. But for the time being, everything is still relatively simple. Now, what can you do? Well, with these Poisson brackets, you can write down in a succinct way the equations of motion of your dynamical system, the so-called Hamilton equations, using them. So Hamilton equations. Of course, you are after solving the dynamics, so you're interested in solutions, which means, how do the coordinates and the momenta depend on time? I mean, you're looking for trajectories on phase space that give you solutions. And using these brackets, this is what the equations look like. So there are a bunch of first order equations. Qi dot is equal to Qi Poisson bracket with H. And Pi dot is given by Pi Poisson bracket with H. Now, if you plug in this definition up there in terms of the partial derivatives, you see immediately what this amounts to. This is just partial derivative of H with respect to Pi. Of course, you get only one contribution because, where the partial derivative sees this Q and sees the P dependence here. So for our particular example, this just gives us a Pi divided by M. Now, here of the two potential contributions, there's only one where the del by del Pi sees this, and therefore the del d by dqi sees this here, and I get a minus sign. And what this is, of course, it just sees the potential part of in the simple problem we have looked at. So it's this. So this is a set of 2n first order equations, and that's, of course, the essence of what the Hamiltonian equations of motion are. If I now substitute one in the other, because here I get a Pi on the right-hand side, and here I get a Pi dot, right? If I just substitute this in here, I get a Pi dot equal to M Qi double dot, substituting this into Z, equal to minus del V by del Qi. And of course, here you see exactly the standard second order equations of motion as I would derive them directly from the Lagrangian. So here you have the equivalence of having substituted a set of n second order equations, which are those, by a set of 2n first order equations in time. So that's a characteristic a feature of the Hamiltonian dynamics. Now, in order to prepare a little bit the case we'll be discussing, where we have constraints and associated gauge symmetry given on this phase space, let me introduce something that is called the vector field associated with a given phase space function. So there, what one is using is really that a partial derivative can be interpreted as kind of a vector field, a directional vector field on phase space, on configuration space. Yes. And given the Poisson bracket structure, there is a natural association of any phase space function with such a vector field, kind of a direction in phase space. So a vector field, as a matter of fact, on phase space. And that's called the Hamiltonian vector field associated with a given phase space function. And as part of this, I urge you also to think of the coordinates, the Q's, Qi's, and Pi's, as particular cases of functions, namely the coordinate functions on phase space. because to them in particular applies this construction. Yeah. So what is the association? It goes as follows. So for each function in C infinity S, one has an associated so-called Hamiltonian vector field. Vector field. And the vector field is given by, well, the notation is a capital X, and the kind of the functional argument appears as a subscript. And by definition, it's equal to F, well, the Poisson brackets, where I've just substituted the function into the first slot, into the first argument. Now, what does that look like concretely if I'm in Darboux coordinates? It's a sum over I partial F del by d by dqi d by dpi minus df dpi d by dqi. So you see, because I haven't placed here another argument, kind of these derivatives just appear by themselves. But of course, I can think of these as, elementary vectors in the coordinate directions, right? So it's a vector field. So here one is making use of this dual interpretation of a vector field, or even a vector, as kind of a directional derivative on your underlying space, right? So one can go back and forth between those two interpretations. But it's also clear now that, so with every f, this gives me, of course, a vector field. You see, I give you a vector field if I give you the components in the basis qi of the vector. So the vector has 2n, has a basis of dimension 2n, and these partial derivatives can be thought of as a basis, and I just have to give you the coefficients in the basis, and the coefficients are exactly given by the partial derivatives, which themselves, of course, depend on q and p. Yeah, is that clear, what this is geometrically? Well, you make use of that a bit more later when we come to this generalization. Now, now we have this classical structure. We have phase-space functions. They satisfy an infinite dimensional Lie algebra. And the question is now, how much of this structure can we carry over to the quantum theory? Now, what one usually calls kind of canonical quantization proceeds formally as follows. Schematically, as I said, by putting heads on things, right? Qi's become Qi heads, Pi's become Pi heads. This Poisson bracket structure, one would like to map onto the commutator bracket of the associated self-adjoint operators associated in general with, well, certainly with these coordinate functions, but hopefully with more general objects also. And that, of course, leads me to the, as we had already on the blackboard, I think, a few times, the canonical commutation relations for the elementary self-adjoint operators, Qi and Pi. A Qi hat with a Pi, Qi with a Qj hat gives 0. A Pi hat commutator Pj hat is also 0, and a Qi hat with a Pj hat gives IH bar delta Ij. Now, you're used to these relations as just being satisfied in kind of the standard representation on square integrable functions. One usually works with in quantum mechanics, in finite dimensional quantum mechanics. Now, one can turn this thing around and say, now, how many quantum representations are there of these classical Q's and P's that will satisfy these commutator algebras? I mean, how many representations in terms of self-adjoint operators are there which satisfy this? And the answer is, well, there is essentially one. So that's so a result I have already mentioned to you last week at some stage, but it's very nice because it's a uniqueness, it's a uniqueness theorem. So you don't have to think long and hard. Now, what quantum representation am I going to choose? Well, there is just the one. So that takes the form of a mathematical theorem. So these things have essentially, so they have a unique representation in terms of self-adjoint operators. I mean, of course, the Q's and P's, in terms of self-adjoint operators. And so the theorem I quoted to you is also called the Stone-von Neumann theorem. So in the old days, I would have given you a reference, but nowadays you do just Google Stone-von Neumann, and you will learn all about it. Okay. So why is that nice, this uniqueness theorem? Well, it tells me, of course, you see, quantizing a system is not just quantizing the elementary operators, these Q's and P's, but of course what I'm after primarily is a dynamics, a quantum dynamics associated with the classical dynamics, which was given to me as a Hamiltonian function. So that's, of course, another phase-space function. Now, using this uniqueness theorem, one again obtains an essentially unique operator, H hat, which is just given in terms of these elementary objects by sum over pi hat squared plus v qi hat. So that's unique. Of course, this was a very simple example. And we ended up essentially, of course, now this is as you've said many times, I mean, now diagonalizing this, finding the eigenstates and eigenvectors, I will have solved the quantum problem. How representative is that for the general case? The general case means general phase spaces and general dynamics in terms of, well, a more general class of Hamiltonians. Now, it turns out that it's not very representative. It's a simple example where this apparently goes through nicely and essentially uniquely, but this is not true for general classical dynamical systems, in this case given to you in a canonical formulation. Now, however, posing the question goes by the name of Dirac. So that's kind of the Dirac canonical, I should put here, canonical quantization program. So he was among the first people who thought about this systematically, asking, can we elevate this to a general prescription? Elevate this construction to a general prescription. So what do I mean by this construction? This construction meant I have a classical phase space given. I have a Hamiltonian. And can I use kind of this, can I think of that as a rule? You know, I just substitute these elementary functions, coordinate functions, and, well, then I stick this into the Hamiltonian, and I'll get an essentially unique quantum theory. And as already anticipated by my earlier comments, the answer is no. In general, this just doesn't work for a whole bunch of different reasons. So Dirac himself already realized fairly early on that certainly if one was thinking of kind of generalizing this substitution rule for general functions on phase space, that you actually immediately run into contradictions with at the level of the commutator algebra. Because the classical algebra of the phase space function just has a definite form, and it works for any two functions. And then you get a specific right-hand side. The question is, can I make a consistent assignment, you know, where now to every classical phase space function, I associate a certain self-adjoint operator in such a way that the algebra is preserved. The entire algebra, infinite dimensional algebra of this algebra here is preserved isomorphically in the quantum context. Well, there are various problems with this. One of them is a so-called factor ordering problem. I mean, this is how it concretely appears as a problem. Now, let me phrase the question about the existence of a quantization prescription in the following way. Is there what we are going to call a quantization map? A quantization map. Let me call this capital Q. That is a map from the phase space functions into the self-adjoint operators. Let me just abbreviate this SAO on some associated Hilbert space curly H. In such a way that with this F is associated some self-adjoint operator, which I simply call F hat, as usual, such that the following holds simultaneously. 1. For the coordinate functions, I have the usual kind of Schrödinger representation on wave functions of Q. So they are represented by multiplication. That's, of course, a familiar property from usual quantum mechanics. For the PIs, I get an association with PI hats, self-adjoint, which act on my square integral wave functions, again, in the usual way, as partial derivatives with respect to Qi of my wave functions. Now, I should also say here the self-adjoint operators. Of course, by this I mean so operators on the square integral functions on Rn with respect to the Lebesgue measure satisfying F dagger equal to F. So that seems a reasonable condition. So that's what we have for standard quantum mechanics. Now, the second is that if I now look at an arbitrary pair of such phase space functions, then of course via this quantization map I can associate it with them two operators, f hat and g hat, and obviously I can take their commutator. Now the question is, can I always achieve that this is equal to I h bar, the classical Poisson brackets, which of course give rise to another phase space function? If I now apply my map to those, is that the same? So in a way, is it a commutative diagram where the two operations are the quantization map, putting hats on things, and taking the commutator or Poisson bracket respectively? So does such a thing exist? So unfortunately, the answer is, well, I don't know whether unfortunately, but that's how it comes out. The answer is no. And it's no even if we confine ourselves, say, to polynomials in the basic Q's and P's. So not even, it's not even true if we confine ourselves to polynomial functions of the basic phase space coordinates qi and pi. And here there is another theorem for you to Google. So this statement is the Grunewald von Hove theorem. You know, I live in Holland, so I'm very happy to teach you how to pronounce this. Oops. Now, there are two versions of it, 46, 1951. And there's also a bunch of kind of more precise technical specification, which I skipped here, but which, well, are not essential for what we're doing, what I'm trying to explain. Dennis, do we still have this exercise? Okay, great. So you'll be figuring out what exactly the problem is. In a nutshell, so even if you restrict yourself to polynomials, the problem is, well, factor ordering problem refers to functions where, you know, you have mixed terms in Q's and P's. Well, preferably, which do not Poisson commute. Right? So then the issue is, of course, classically, these things do commute, but quantum mechanically, they will no longer commute. So there arises an ambiguity. That's the first thing you notice. There arises an ambiguity of how to quantize an expression like this. Is it Qi, Pi? That is not the same as Pi hat, Qi hat. And that's not the same as, say, 1/2 Qi, Pi hat plus Pi, Qi hat. So there's an ambiguity. So this, which is clear, which will appear every time you have such products. Then the next question is, can I find a prescription that uniquely nails down? Maybe can I find, you know, anything that on the quantum side, you know, fixes, say, as a totally symmetrized expression, you know, what I want to use there. But then the problem is, then in general you'll mess up your quantum commutators. They will no longer be isomorphic to the classical structure. Oops, my goodness, time is running. Now, what more did I want to say? Thankfully, not much more. Just one remark is that, well, you can say, well, maybe after all, but is that something I really need? Maybe it's an academic problem, and if I look at physically interesting Hamiltonians, well, I never run into this trouble. Clearly, I mean, for the harmonic oscillator Hamiltonian, or for a simple a particle in a simple potential, this problem doesn't seem to bother us. The fact that you cannot translate arbitrary phase space function, because usually you're not interested in those. Now, the trouble in gravity, kind of put in a nutshell, or one of the troubles, is that a typical gravitational Hamiltonian. So if you strip it to the bare bones, and if you adopt classically a Hamiltonian language, it's typically of the form, well, f. I mean, these are not the perturbative f. So these are just some coefficients, Fij, Qi, Pi, Pj. It typically has kinetic terms that are of this form. So they are p-squared type terms, which is kind of to be expected, but they have q-dependent coefficients. And you see, then you are immediately in this troublesome case here. So, of course, here I'm writing down as if it was a mechanical problem. So if you say, look at quantum cosmology problems, it will look like this. You will get this structure. But if you go to the field theoretic case, you will get the same observation will apply for the fields, and you will run into factor ordering problem. So that it gives you one first glimpse of why gravity is somewhat different from other theories, and you run into troubles which you don't run into elsewhere. Okay, see you tomorrow.